linked list implementation of a stack. Now, the nodes in the linked list each have two variables. One variable is the actual item, which would be a letter in this case. The other field is a pointer, which then points to the next the next node. And notice that the last node here has a pointer which is null. This represents a null pointer. Now there is also a variable pointer type which points to the whole structure. We could call that head, or we could call that top, but the important thing, it points to the top item in the stack. If the stack is empty, then the value of this particular variable is null. All right, now let's see what happens when you delete something. Suppose, for example, we want to pop. If we want to pop, what we do is we return the top item, E, but then we redefine the top item to be that, which means that this pointer is altered, so it now points to the next item. Now, if this were the only item, this would be directed to null. What it does is it copies the value of this pointer into this particular variable. So now the stack has one fewer element. All right, now let's look at how we do push. So let's say we do push, and we're going to push the letter, I think it was D, wasn't it? So therefore, what we're going to do is, this would be done in a subprogram, which means that we would now have local variables. We would create local variables, and we would put a D here. Then the pointer field of this local variable D would be copied from here, copied from the head item, and there it would be. Now, this is a dynamic variable. It's not really local in the same sense that this one is. And so it won't go away when we leave the procedure. But what's important is this does go away, which means that we have to copy this variable here, the variable from the temporary pointer, into there. So that means that this particular pointer will be deleted, or actually reassigned, and will now point to that, because we're now copying this value into there. And now we have pushed D. So now the current stack has D as the top element, then F, then L, then A. Now we're going to do the last problem here. We're assuming that we have a weighted directed graph with n vertices. And there are m edges, directed edges, each of which has a weight, W. Now, in my answer sheet, I got capital F and capital V mixed up. So the output is not the arrays V and B, it's going to be the arrays F and B. I'll make the change in the document as soon as this is over. All right, now the black represents what was already in the test. And I asked you to do a back pointer, and the answer is the back pointer is right here, because if you choose to redefine the shortest path from V1 to Yj, for example, now Yj could be V31 and Xj could be V18, because every vertex has a name Vi for some I, or Vj for some Ij. However, for every edge, there are extra names for the vertices, the Xj and Yj. So one vertex could be X7, it could also be X23, and it could also be Y15, all at the same time, that it was V20. All right, now, since I made the change, first I checked to see if this is greater than that, which means this is a better choice. So we update it that way. Now the back pointer since the new path from V1 to Yj will have the edge here as its last, the edge here as its last edge, the back pointer of Yj will change to Xj from whatever it was before. Could have been undefined before. All right, now let's look at the red stuff. The red stuff is to short circuit the outer loop. So the outer loop executes n times, actually n minus 1 times, because the longest, shortest path could not have more than n minus 1 edges. However, the longest, shortest path could have far fewer than n minus 1 edges, and we want to short circuit the loop if it's already finished. So we have the Boolean value changed, and then we test the value change to get into the main loop. Now, since we want to do it the first time, we have to make change true, otherwise we'd end here. Now, what change indicates is that some value of f has been changed during the execution of this particular iteration of the outer loop. Now, you notice that t doesn't occur in the code, it's just a clock. All right, so we first have to change the value to false because so far there have been no changes in this particular iteration. So we then go through the relaxation process here. We have an if condition, and if this is true, we do all three of these things. Notice that one of the things we do is we change the value of changed to true, because we did actually update a value of f. That means that the next iteration of the outer loop will actually execute.